Good afternoon, ladies and gentlemen, to this online session about how to ensure the high wind loads are sustained by your solar trackers. This is a very technical, specific online session that we hope that can help you resolve those questions that you have. And with us today, we have three experts that are going to help us and share knowledge with us today. And I'd like to welcome them and ask them to introduce themselves so that you can get to know them a little bit better. So Sergio, please, if you could unmute your microphone and introduce yourself shortly.
Yes, thank you, Belén, for the kind introduction. Thank you very much, everybody, for joining us in this session. As you said, Belén, my name is Sergio Jimenez, and I'm the responsible of the engineering department in STI Norland. That, as you know, is a solar tracker and fixed structure manufacturer company. Just let me highlight 3 or 4 of the last goals of the company in these last days. Up to now, over 6 gigawatts of solar projects have been designed, manufactured and supplied. Early next year, STI Norland will reach its 25th anniversary. And finally, as many people may know, STI Norland is pioneering in the design and development of the D-Road solar tracker concept, known as STI H250, that in the long run has been proven to be a winning solution. So thank you very much to everybody. Thank you, Belén.
Thank you very much, Sergio, for joining us today and sharing with us your know-how. We actually have people from, I've seen Morocco, some representatives from Aqua Power, and someone that is saying that this is a very important subject. I agree with you, Carlos, so don't worry, we'll get to it. Next, I'd like to ask Antonio to please introduce yourself as well.
Thank you, Belén, and thank you, everybody, for being with us. But my name is Antonio Alvarez, and I'm a doctor in civil engineering. I have finished my PhD last year, and at the moment, I'm a research engineer in the University of A Coruña.
Thank you very much, Antonio. Also, next to Antonio, you can see Juan. Please, Juan, can you introduce yourself?
Hello, everybody. My name is Juan Quintela, and I also work in the University of A Coruña in the structural mechanical group. I'm working on my PhD right now about optimization of parameters of long span bridges.
Excellent. Well, welcome to the 3 of you. As you can see, Antonio and Juan are wearing masks. This is because they're together, and we have certain security protocols here in Spain that we have to follow, but they will actually do the presentation without the mask. So for now, I'd just like to ask Sergio to please unmute your microphone to prepare your presentation. And whilst Sergio is preparing his presentation, I'd just like to give you a few reminders and recommendations. You've already heard it, and many of you already have been to our webinars, but so we're going to have 3 short presentations, and we'll follow these with questions. The questions from you. Okay, so to send your questions, don't use the chat. In the chat, you introduce yourself, you tell us about you, and you can comment whatever you like, but actually use the Q&A box at the bottom, because it's easier for us to manage the questions that we have. So please just send your questions, and we'll get to them at the end. We reckon we'll have at least 15 minutes for that. And just a note, we are recording the session, so you don't have to worry. You can catch the recordings after. You can send it to any colleagues that you have if you see anything interesting. And we will also send you a link to download the materials that you're seeing on screen right now. Sergio, Antonio, and Juan have their contact details also on the materials, so you'll be able to contact them thereafter. Okay, without further ado, Sergio, go ahead. The floor is yours.
Okay, thank you. So there we go. I will say that the main objective for today's session is to share with you all the knowledge that we have developed in the company during this past month in material wind design. In particular, I would say in tracker wind design. 3 are, under our internal point of view, the main ideas that everybody should take into account when dimensioning a solar tracker and validating its design. Firstly, regarding ABL atmospheric boundary layer wind tunnel test, it is a must to have a proper definition about the terrain category for which it has been developed. Therefore, also wind directionality and pressure zoning must be considered. In addition, and in relation with the tracker structural design and dynamic structural calculation, it is needed. It's what internally called in STI Norland dynamics on. For such calculation, we consider necessary to characterize in advance the damping ratio of the solar tracker, not only for main torsional, but also for main sectional modes, and consider the associated dynamic amplification factors. Another important question to take into account is the necessity of building up an appropriate 3D model that also includes, among others, the center around the slopes and the installation tolerance allowed for the tracker. And finally, all tracker design needs also to consider critical wind velocity aeroelastics analysis. So, starting with the terrain category, all structural calculation standards such as Eurocode and ASTI define a classification of the terrain based on its equivalent roughness. For example, open sea, flat terrains, urban areas, and so on. The most considered within the solar sector are type 1 and 2, according to the Eurocode definition, and type C, according to the ASTI, all of them for flatter terrain situations. For these three types of terrain, you can see in the figure represented on the left, the speed profile of wind that they generate in high. So these profile are later simulated in the atmospheric boundary layer tunnel test by means of elements that artificially generate the desirable roughness. Oops, sorry. There it is. Okay, it can be seen that the flat type C terrain generates a wind profile higher than the flat terrain type 2 or type 1 at the typical height on around 1 and 1.5 meters. This is much more evident when we translate from velocity profile to pressure profile. In the figure on the right, you can see a comparison with respect to the profile of type ground pressure C. A type 2 terrain generates almost half of the pressure of a type 1 terrain on a tracker. Furthermore, since in most atmospheric boundary layer tests, the pressure confidence are obtained referencing to the speed measured at the height of 10 meters, this means that an ABL wind tunnel performed with a type 2 soil returns period coefficient that can be almost half as small as those that will be obtained in an equivalent test for typical terrain C, as you can see in these two graphs. Okay? So, the terrain category not only influences in the values of the pressure coefficients that are obtained in an ABL wind tunnel test, but also in the reference pressure values used for the calculation. For example, in Pamplona, where STI in Orban is located, for the same wind zone, in this case, according to the Eurocode, a basic speed of 29 meters per second is defined. The design pressure will be higher for type 1 versus type 2 terrain. In a relation, in this case, on 1.34 times one for another. So, continuing again, considering the relation with the terrain category, it's not always easy to give a precise answer regarding which category should be considered for a certain or determined project site terrain. The regulation gives some guidelines, but the reality, on the contrary, is complex. Anyway, what we must always keep in mind is that the correct definition of the terrain category of the project site is critical. That's the key, since it affects both to the results of the wind tunnel tests and to the reference pressure for calculation. The difference in design loads between category 1 and 2 terrain can be almost double. For example, 1.22 if we consider category 1 against category 2. The difference in design loads between, this means that a tracker designed according with category 2 terrain values in a location with real category 1 or C is totally underdimensioned, as you can imagine. It can be affected then by twice the strength for which it will be designed. And not only is important the terrain category, but also there might be some site conditions such as topographic accidents, hills, and escarpments that can increase the design with the speed sustainability that must be taken also in account. For example, for this terrain profile, the wind speed is multiplied by a factor of 1.6. Thus, design with action uncertainty is a function of multiple variables. For example, the terrain, the wind directionality, pressure coefficients, local topographic effects, reference pressure, and so on. And the question is, how do we at SATN Norland address this uncertainty to guarantee a design 100% reliable? ABL wind tunnel with category C terrain. With this strategy, we are happy and we are confident that we cover all terrain category scenarios, our possibilities. Analyzing the full range directionalities or wind directions, considering the effects caused by the local topography in our designs, and also making use of the reference pressure according to the project technical specifications. In relation with the wind directionality, what we have to say is that, as commented previously in our atmospheric boundary layer wind tunnel test, we have analyzed the full range of wind directions over a portion of a solar field. That is a total amount of 36 wind directions. I have to highlight in this regard that the most unfavorable direction is not always 0 or 90 degrees. There are some areas and rows of the solar field where the most unfavorable direction is an intermediate one between the previously referenced angles. Okay. Another question is, well, in this slide you can perfectly notice some of the images of the boundary layer wind tunnel test that we carried out in the past in the Polytechnical University of Madrid facilities. We have to highlight in this regard the extensive number of cases that were analyzed in that testing campaign. We analyzed 2 geometrical configurations, the full range of attacking angles and wind directions. So in the overall view, this represents almost 1,000 cases tested. We also consider for the full solar field 5 rows of fully monitored trackers with a total of 500 pressure taps. That means nearly 100 pressure taps per row. Okay. Another important question is the pressure zoning. Regarding pressure zoning, and thanks to the high resolution of the metering that we carry out, we have been able to characterize both global and edge effects on the main structure, such as local effects on the purlins. We have also obtained the values of the dynamic amplification factors for all the cases tested and for different damping levels, both in flexural and torsional behavior of the tracker. Okay, in relation with structural damping, one of the most important things to talk about is that both torsional and flexural damping values were obtained through a vibration test carried out on field over full-scale tracker prototypes. In this slide, what you can see is the results of some of these tests. it can be noticed that the torsional response of the tracker with values in between 10 and 20% means that the tracker is highly damped against this behavior, torsional behavior. On the contrary, we got vertical vibration we found out that vertical vibration has a poorly damping response, taking values in the order of 2 to 3%. Okay. We carry out what we did when having to answer to this question of perfect characterization, not only the, let's say, the dynamic behavior of the tracker, but also the damping characteristics. We carry out the vibration test using our own system of capturing movement performed in a slow motion way, through which we manage to capture displacement and velocity for multiple targets placed along the tracker under testing, as you can see here in the images. It can be seen on the right of the motion capture on these pictures, 7 targets from one of the torsional triads on the left and 3-dimensional reconstruction of the position of the aforementioned targets during the tracker vibration. We also perform vibration tests to obtain damping values associated to bending moments, bending modes, given in high impact they have on the dynamic amplification factors by taking relatively low values. As a final conclusion, we strongly discourage using bibliographic values, usually in the order of 5%, that lead to unconserved reduction of the dynamic design loads. And finally, as a summary of what we have seen up to now, we include all these keys in our structural designs, offering a product with high reliability. Our calculation modes include pressure zoning, outside and inside row strategy, effects, effects, pressure peaks, and so on. We use the design envelope with the most unfavorable tested weight directions, and we include dynamic amplification factors corresponding to the values of torsional and flexural damping directly obtaining by vibration tests performed over real-scale prototypes, as shown before. Also, and I would like to highlight this last question, our calculation models correspond to the reality of what is offered and finally executed in relation with the tolerances and implementation slopes. What does that question mean? For example, slopes and implementation tolerances have a great influence on the design since additional stresses appear on the structure. You can see this effect very visually well. Here you have an example of an optimized typical tracker without considering implementation slopes and tolerances. Every single component is below 100% of a structural checking ratio. But on the contrary, what happens when in the same model, 10% of north-south slope is implemented? The consequence is that the structural elements happen to occur over 1.30 or 140% checking ratio, as you can see in this picture. So this effect can be detected in the results of a model calculation. In this case, for example, in the structural model without the slopes, the support only takes bending stresses along its strong axis, remaining at 96% of its mechanical capacity. But on the contrary, on the right side of the slide, we can see a detailed calculation report of the structural model with a slope. And an additional bending stress appears over its weak axis, growing up to 140% of its mechanical capacity. Okay, going to the aeroelastic design, first of all, I would like to introduce what the aeroelastic instability means, to have an overview idea of its meaning. As you know, and as you quite know, is the aeroelastic instabilities are one of the main causes for damaging and collapsing solar trackers. So what is the aeroelastic instability? In a simplified way, it could be summarized in a sentence. At a certain value of a critical speed, for example, this one, the wind introduces negative damping in the structure. What do we mean by negative damping? Many of us are used to or have heard about positive damping. But the positive damping is somehow what water means for fire. It causes the kinetic energy of a moving system dissipates until it stops moving. This is obviously a good damping that makes dynamic amplification factors lower. On the contrary, in a complex system where the structure and fluid, in this case the wind, interact in nonlinear way, damping can take negative values. When this happens, the negative damping, instead of being water, it becomes gasoline for fire. In each vibration cycle, the wind introduces kinetic energy into the system, amplifying as consequence the vibration until it breaks down. Okay. The basic idea for the aeroelastic design is to obtain the wind speed, known as critical speed, for which damping becomes negative. Generally speaking, this critical speed refers to the average speed of the height of the structure, in this case at the height of the axis of the solar tracker. However, solving the analytic problem of the aeroelastic calculation is not as simple. Firstly, because in order to solve this problem, it is necessary to measure experimentally in an aeroelastic wind tunnel a series of functions called flutter functions or flutter derivatives to be able to assemble both the stiffness and the aeroelastic damping matrix. Summarizing, we can talk about three elements necessary to obtain the critical speed of a three-dimensional structure. First of all, as previously said, we need to measure the flutter derivatives of the tracker in an aeroelastic wind tunnel, which we have done for different configurations, both for outer rows and inner rows, and for the tail range of attack angles aware. Secondly, it's necessary to perform a 3D structural model to define the mechanical and dynamic tracker behavior, geometry, stiffness, mass, damping, and so on. And thirdly, we need an algorithm or a solver to solve the problem of nonlinear eigenvalues that results from assembling the stiffness and damping aeroelastic matrices over the 3D structural model of the tracker. Which are the advantages of this methodology based on the flutter derivatives? It is a methodology well understood and established in other fields of the civil engineering for decades. We are, how not to say it, we are not investing in anything new by relying on existing knowledge. It is the most reliable and accurate method to characterize the aeroelastic instability of a three-dimensional structure, and it offers great flexibility when designing, since it allows modify the geometry and structural parameters of the tracker. But on the contrary, for applying this method, some requests are needed. The main ones are: it requires a relevant obtaining of the flutter functions in an aeroelastic wind tunnel, and this is why we have been in contact with the University of La Coruña. Antonio will explain as well later on about this methodology and about these facilities. We need also a specific calculation software to solve the complete problem and to obtain the associated critical speed. We have also developed our own calculation software called the Solar app, focused on solar trackers design. And just to finish my presentation, I would like to show you a couple of screenshots about our Dena Solar app software in order to have a quick overlook about how it looks like. Thank you everybody for your kind attendance. Helen, I'm ready to go
To answer the questions. Excellent. Thank you very much, Sergio. I will fully admit, you guys, I am not an engineer. I do other things. I have other gifts, but not this one. It's a lot of math. There are a lot of questions already waiting for you, Sergio. You can start up on those and we will have some more thereafter. You guys don't keep any doubt to yourself. Please send them through the Q&A box for Sergio. Because obviously this is a very specific technical issue and we must make sure that your questions get the correct answers. So thank you very much, Sergio. Antonio, I'd like to invite you now to give your presentation. I know that you're next, and then Juan. So please, if you may, I know that you guys have been sending things. Please don't hesitate to send some more. Sergio is going to be on answering duty, and then we'll have Antonio there as well. So Antonio, please unmute your microphone, share your screen. And for all the people who've joined us recently, our numbers have been growing. Don't worry, we're recording this session. You'll have the opportunity to watch it again if you choose to, and you'll also have the opportunity to check the materials that you're seeing on screen. So Antonio, you ready?
Yep.
Off you go.
Okay. As we were saying at the beginning, we belong to the structural mechanics groups of the University of A Coruña. And among other activities, we do dissemination through the organization and participation on international and national conferences and courses. We also have publications of books, technical reports, and especially in scientific articles. We also develop software for suiting our needs and the needs of our clients. We are proud of having collaborated with a wide range of companies of different sectors, among them aviation, transportation, construction, and energy generation. And we focus on research in the fields of aerodynamics and aeroelasticity, seismic analysis, structural optimization, geometry and material nonlinearity, and contact, among other fields. And if you want to know more about us, you can check our webpage. When we are trying to perform aerodynamic or aeroelastic research, we use a combination of numerical simulations and experimental campaigns. These campaigns are carried out in our wind tunnels. One of them, an aerodynamic wind tunnel, the one you can see on the picture, which is for the study of sectional models. This picture and the one on the left. Here you have images of the solar trackers. Or in our other wind tunnel, which is a boundary layer wind tunnel, which also allowed for the study of full model structures and the reproduction of the wind profile and turbulence intensity. Now, changing to the analysis of sectional models, if we have the model rigidly supported, we can obtain the forces acting in the structure due to the wind. These forces are related, are dependent on the shape and the wind speed. This and hence in the Reynolds number. Usually, these forces are given in their non-dimensional form and are called force coefficients. As we are measuring these forces with balances, we are able to capture both pressure and viscous forces. And if we analyze these force coefficients further with respect to the angle of attack, it allows us a priori to determine to which region the structure may be prone to suffer flutter, which is in this case related with the regions in which the slope of the force coefficients is negative. It would be, for example, this size. Also, it is a more complex analysis, but a priori is for the angles of attack that we may be cautious. Also, when you have a body submerged on a fluid, it starts to develop a boundary layer. And if it separates, it generates vortices which are going to be shed on the wake of the body. These vortices exert periodic forces over the structure that may lead to vibration. In order to obtain the frequencies of the vortex shedding, you have to analyze the spectral density of the force coefficients. When this vortex shedding is near the natural frequency of the structure, or to a subharmonic or superharmonic of this frequency, the locking phenomena takes place. This phenomena is for reduced wing speeds, and in this region of reduced wing speed, the vortex shedding is captured by the natural frequency of the structure. And also, when this happens, the structure experiences vortex-induced vibrations, which are self-sustained oscillations, which may lead to serviceability and fatigue-related issues. Finally, when instead of having the sectional model rigidly supported, you can support it by means of springs, allowing it to freely oscillate with 3 degrees of freedom. These oscillations allow us to calculate 18 non-dimensional functions, which depend on the wing speed and the frequency of vibration. These functions are called flutter derivatives, and they allow us to relate movement and aeroelastic forces, which will be needed in order to analyze if the structure will be prone to suffer other aeroelastic instabilities, which now my colleague Juan will be telling you how to calculate. You just give us a minute, we will change, and Juan will begin his presentation.
We've lost your camera, guys, as well in the switch over. So, okay, here we go.
I'm just to change so you can see me.
Okay, Juan, go ahead.
I'm going to continue the presentation, and I'm going to explain a little bit about the structural models and some aeroelastic phenomena. The structural models were made considering 2 lines of panels connected by a rod mechanism. Frame elements were used for the substructure, while the panels were modeled with shell elements. 2 configurations were considered with different dimensions, different width, height, and distance between lines. Configuration 1 has a width of 2 meters and can be seen on the left, and on the right, the configuration 2 has a width of 4 meters. Several angles of attack were considered, and we can see on the bottom the different models for each case. The angles considered were 10, 20, 35, and 60 degrees, and the negative ones. For all these models, a modal analysis was performed to obtain the natural models and natural frequencies. In the table, we can see the natural frequencies obtained normalized to the first frequency. And in the picture below, we see the first natural modes. For all the cases, the first natural modes obtained were torsional. And we can see that for each mode, only one line of panels moves, while the other has no displacement. All these results were used in the analysis of different aeroelastic phenomena, like vortex shedding, torsional divergence, and flutter. As I said, one of the aeroelastic phenomena studied was torsional divergence. In torsional divergence, we try to find the critical speed that causes a moment that the stiffness of the structure cannot resist. In general, wind creates a drag, a lift, and a moment. This moment creates a rotation around the axis, and so the initial inclination increases. When this inclination increases, the moment decreases again, and the inclination increases again, and so on and so on. So we have to find when the situation converges and what is the total final rotation. The study was made for different inclinations of 4, 10, 20, and 30 degrees, and different wind speeds of 15, 30, 45, and 55 meters per second. In the picture, we can see the additional rotation obtained for different wind speeds for the case of 10 degrees. And we can see that the additional rotations increases significantly for high wind speeds. The other aeroelastic phenomena study was flutter. Flutter is an aeroelastic instability in which the interaction of the inertial forces, the aerodynamic forces, and the elastic forces causes a structure to perform undamped oscillations. The problem consists in solving the dynamic equilibrium equation, in which the acting forces are the aeroelastic ones. These aeroelastic forces depend on the flutter derivatives and modify the stiffness and damping of the structure. In the case of the solar trackers, 2 mechanical dampers were added to increase the structural damping. So a new matrix C sub M had to be defined to include the damping of these mechanical dampers. The problem is a nonlinear eigenvalue problem, whose solution is dependent on the flutter derivatives and the wind speed. The solution gives us the critical wind speed, which makes the damping of the structure null. For the solar trackers, 72 analyses were performed with different combinations of natural modes. All the angles of attack for both configurations were analyzed, and with and without the inclusion of these mechanical dampers. In the table, we can see the results of the critical wind speed normalized to the case of 0 degrees. And we can see that in general, the critical flutter speed increases with the angle of attack. In conclusion, the collaboration with STI Norland has been in the form of multiple experimental tests to characterize the behavior of solar trackers. And the results obtained allow us to conclude that these solar trackers present good behavior against vortex-induced vibration, torsional divergence, and flutter. And with this, thank you for your attention, and we are ready for your questions.
Thank you very much, Juan. And also thank you very much, Antonio, for your presentation. We have a lot of questions, right, Sergio? You've been answering some of them by text.
Yeah, I've been trying to do my best, but you know, it's not easy.
Oh, no, absolutely. And some of them, they're probably complicated to explain. I mean, luckily, we have good 15 minutes that we can use. We have at the moment 9 open questions. So I'm going to start with a couple of them that you've marked, like you'd like to answer. So I'm going to start with those. And then once we've done those, then we'll open up to the rest of the questions, also with Antonio and with Juan. I just want to let you know that I need your help, guys, because I understand, you know, solar technology well enough, but this is very, very specific and very, very in-depth. So I may not understand everything. So, okay, Carlos is asking, and 1V and 2V configuration, and you wanted to answer this live. So go ahead, Sergio.
Yeah. Well, regarding this question, we performed, I think it was shown in my presentation, we performed a full amount of tests in both tunnels, like La Coruña and Madrid tunnel testing, for both configurations. When we've been talking about 2 configurations, the first one is associated with the 1 portrait and the other one for the 2 portrait. One of the most important things I wanted to highlight is regarding the aeroelastic wind tunnel test is that it only depends, this methodology based on the flutter derivatives, only depends on the aerodynamic profile. One of the pros is that you just only have to add the tracker characteristics, both in mechanical, in terms of dynamic and damping radius, and to include them in the movement equation in order to solve the full problem. So we perform, as I said before, the test for both for the 1 portrait and 2 portrait configuration, and we have a wide range of testing that allows us to go for any kind of tracker solution. That will be the answer for that question.
There is more, don't worry. More where that come from.
Yeah.
What's the stow strategy of STI?
Okay, at this moment, our stow strategy after developing this wind tunnel testing campaign is to go through a 25 degrees the position windward. What means with the upper face of the modulus pointed against the direction of the wind. So the effect of the wind applying or acting over the upper face of the PV modulus will be pushing the whole tracker against the ground. So this is our current stow strategy.
There's another one here that says, whoa. And by the way, Juan, Antonio, feel free, if you want to add anything, just let us know. I'm going to throw the questions out there. I don't know who they're best directed to. I mean, this one says, dear Sergio. So, I'm pretty sure it's for Sergio, but just feel free to add. What would the damping percentage be considered in your assumptions?
Yeah, that's a good question. Firstly, I have to clarify that there is no assumptions coming from our side. I mean that we have perfectly characterized the damping characteristics of the tracker because we have developed testing on real scale trackers here in our facilities in Pamplona. So we have obtained both the damping characteristics of the tracker, not only for torsional modes, but also for flexural modes. And one of the most important things I have to highlight in this session is that because usually this kind of this typology of the structures has the damping factor, rotational damping factor in between 20 and 30%, this leads to have very low damping or amplification damping factor, dynamic amplification factors. Nearly or all of them are mainly below 1. On the contrary, the most important thing is to consider the flexural damping factor that in our case is between 2 and 3%. In our case, I'm quite sure that in the rest of the tracker solution in the market. So the question is that if you are considering, and for that kind and that 2 or 3% of flexural ratio, the amplification dynamic factors come over 2. So that's quite a lot. The question is that if we consider, because of the bibliography or technical bibliography, a damping factor around 5%, you are infradimensioning the structure because you are getting a lower dynamic amplification factor. So that's quite important, not to determine it according to a specified bibliography, but testing on real scale prototypes.
Antonio, Juan, did you have anything to add here? Or shall I continue? No? Okay. Mark Mijos, which is an old friend of mine, but he's not old. I mean, we've been friends for a long time. Just want to make sure. He asks, both your wind tunnel photos and your CFD figures indicate a limited number of rows available for your studies. Can you describe your ability to assess wind loads deep within a solar field and or impact of wind mitigation features such as fencing or wind blocks? So yeah. I don't know. Yeah, you want to go ahead? Okay.
I'll try. It's not easy to answer to that question. I mean, we have developed our wind tunnel testing, atmospheric boundary layer testing for a total amount of 5 rows that represent with enough accuracy what's happening to the wind or to the whole solar field in terms of wind action. We have to consider that we are only taking into account in the design a single strategy of considering outer trackers and inner trackers at the same time. So for the characterizing and dimensioning the outer trackers, we're considering the first 2 outer rows of the wind tunnel testing and the rest from 3 to 5 or even for 2 to 5 rows. We consider that values coming from the wind tunnel test for dimensioning the inner trackers. So what we have done is just to build up a perfect correlation between our CFD models and the results coming from the wind tunnel testing. So this way, we are able to perform any kind of analysis that in relation with any situation that may happen in a solar field. So our advantage is that at this moment, we have perfectly characterized our CFD models regarding the results coming from a wind tunnel test. And we are prepared, somehow we are prepared to develop any kind of engineering exercise over any accident or any question or any situation that in a solar field may happen. That's what I can say regarding that question.
Okay. Again, same offer stands, guys. Antonio, Juan?
Just add when we studied the sectional model, we have considered one row and 2 rows of solar trackers, and the difference obtained were minor. Then no problems at all should we find with the calculations that that gave us that the structure were fully capable of resist wind loads.
Okay, I keep going, guys. We have another, say, 5 minutes-ish. Abdel asks, have you considered similarities between WT conditions and field conditions? If not, how do these compare to each other? Sergio, I leave it to you.
Sorry, Belén.
Shall I ask again?
Please repeat. I was just trying to read another question here in the chat. No,
don't worry. Okay, Abdel is the second question now on the list. Abdel, you've marked this one. Says, have you considered similarity between WT conditions and field conditions? If not, how do these compare to each other?
Yeah. When I marked this question, I was not sure to understand it. So I'm going to try to answer in a simple way. Is that what we have done is considering the 3 types of terrain category that are described in the standards, the terrain 1 and 2 in the Eurocode, and the terrain category C according to the SC. What we have done is just to perform terrain category C, simulating terrain category C in the wind tunnel testing in order to cover all possible scenarios. So this is our strategy. This way, we are on the 100% reliable situation, covering all possible scenarios. So I don't know if the question was pointing to this answer, but just in case,
We have a more business question, a bit more about the context of the project itself. It says, usually the EPC company, is the one that has to assure that trackers can resist wind peak loads. That is true. I mean, they usually turnkey developments together with the tracker supplier. In prior feasibility phases, like a lean, if you like, or a not very detailed analysis is done with about this. How do you recommend to carry out this issue? How do you do a first like lean calculation without getting in too much detail but still being accurate? It's the first question. Álvaro sent it.
Usually this company
is when you're doing the feasibility studies for a project. You don't usually get into a lot of detail at the beginning?
Yeah, okay. From our side, what we have done is we have a standardized up to 3 types of trackers. Also against 5 types of wind speed. For those, we have developed the full engineering development in terms of calculation, structural calculation, and also detailed and aeroelastic and instability design. So if the question is in the first project approach, how we get to that question and how we solve that, what we can do is just easily go to that standard cases and consider if it resists or not the project conditions, and somehow is a way to solve in the early beginnings of the project or in the early phases on the project to solve all these kind of questions. That is what I suggest.
Yeah, but I mean, it's a little bit of an issue, right? Because when you're developing a project, typically you develop a lot more projects that you end up carrying out. So there's different phases of development. Okay. So just a couple more questions, Sergio, don't worry, and then you can go, because I understand this has been really, really tough now. These questions are very specific. So question, I think is 3 here, says, I'm interested to understand how does STI Nordland come up with a sensible wind speed and direction to determine maximum and design wind speed and wind gusts and how wind gusts are factorized. The question is from Adolfo Guerrero.
How does STI Nordland come up with a sensible wind speed and directions to determine a maximum and design wind speed? Okay, Adolfo, I don't know if you are meaning how we are able to determine for a certain or specific site, which is the wind intensity or the dominant or main wind direction. For such a purpose, we have not by our own, but we have a company, a partner that is able to have a look to the history, to the last 40 years in order to build up an scenario, wind scenario, and just to predict what will happen in the next X years. I mean, according to the life period or to the 300 years or 50 years life period for a certain project. So I don't know if you are asking for that. If not, another question would be, I mean, for every single project, we consider the full wind directions results coming from the wind tunnel testing. That is why we have developed nearly 1,000 cases in the wind tunnel testing. So what we do is just to calculate the tracker for the whole results coming for the whole wind directions.
Okay. I think one more question, maybe 2 if we can. Considering the PV module market evolves with higher wattage modules that have higher dimensions and weight, what could be the tracker evolution technically to adopt, but at the same time, trying to sustain the cost of the tracker? In other words, how are you still evolving your products, but keeping the cost low? Okay. That's what I understand here.
So first of all, just to clarify that there is no possibility of developing the tracker to higher mechanical capacities without increasing cost. That's something that they have to be keep in mind. The question is, okay, one of the best of the pros of this methodology, of the methodology base of the flutter derivatives that were introduced by my own and Antonio, the people, the team in the Universidad de La Coruña give us some deeper details, are based that this methodology requires only to test a prototype, a real scale prototype, a sectional model of the PV model that only depends on the, as I said previously, on the aerodynamic profile of the structure. Then just the problem is solved by introduction the characteristics of the tracker, whatever is its dimension, its size, the mass, damping on the movement equation, and just to solve the eigenvalues problem. So what we are getting in from now is that because not only the weight, but also the size of the models are growing, that these impact directly to the trackers, multiplying by nearly more than the double the wind actions. So I think a new generation of tracker may need to happen or to occur in the coming months. We are working on this based on a new concept. And obviously, I cannot say more about that.
You'll come back and you'll tell us.
Yeah, we'll come back to explain about that.
Okay, last question is one that you've marked as well. And this is a challenge, both for Sergio and myself, because I have to read it. Oh, here we go. For the flexural stiffness and the resulting frequency, is it the flexural stiffness and dampen taken for both the footing and the longitudinal beams on which the panels are mounted, and the interactions between them is Gerrit Crosselar? It's a little bit further down, and seriously, like, there's too many like big words here for me. So go on, Sergio.
Okay. So this is okay. From the technical point of view, I mean, the appropriate way of solving this will be, okay, first of all, you start with a pre-design of the tracker. But obviously, for getting exactly the characteristics of that tracker placed on site and considering the real characteristics of the soil, you need to build up a prototype and test there on site the real damping and dynamic characteristics of the tracker, and then going back and redesign and so on. So, because projects are not solved this way, it is nearly impossible to perform or to act or to manage all the engineering related in this sense. So what we have done is, when we have performed our testing, our dynamic testing of our prototypes here, our real scale prototypes in our facilities, to work under the worst scenario. What this means, that we have considered the wettest models, we can consider the weakest tracker, we have considered the more flexural ground. We have built up an artificial ground in order to obtain, let's say, the less availability or the less tracker capacities, mechanical and flexural and dynamic capacity. And then we have correlated these characteristics with structural models, and this is how we get, this is how we act, how we manage. This is what I can say about this.
Okay, well, thank you very much, Sergio. We've done our best, you know.
I'm enjoying, up to now I'm enjoying at this moment. We can continue, you know.
There are more questions, but we don't have this time. So we'll send these questions to you, and also a message for our attendees. I mean, you have very specific questions. Feel free to get in touch with Sergio directly. His email address and the materials, so if you need an introduction, we'll be happy to perform it. So just get in touch with us. So thank you very much, Sergio, for your time. Of course, Sergio, thank you very much, Antonio, for your time, and thank you very much, Juan, for your time. It's been great sharing with you, and also for the people in the audience. And we will see you in the next webinar. Thank you.
Thank you, everybody.
Thank you.
Bye.